So I'm now going to be maybe over here. Let's put it there. That's not such a small change, but I want to make it big enough that we can see it. Okay? But we'll recognize that this can be as small as we want it to be. What do I call that small change in x? dx. So this distance is dx. Agreed? And what I'm asking is, a small change in x produces how big of a change in area? So that's dA. Agreed? Where dA is the area of this little piece. Okay, dA is this area. If I make a small change in x, if I increase x by dx, how much does dA change? Approximately. If we're going to take an integral, we get it exactly. But if I just want an approximation, how big is dA? Sure. Say it again. Yeah, we're thinking of this as a rectangle, right? If I think of this as a rectangle, it would be this rectangle, wouldn't it? Area of a rectangle is base times height. The base is dx. The height is f at x, right? If I pull this across, that height is f at x. So this little change in area is given by f at x times dx. Agreed? In other words, I could get away with saying dA equals f at x dx. Right? Take the dx to the other side, what do I got? dA dx equals f at x. And what's a? The integral. I get dA dx equals f at x where I know that a is this. So if I substitute this in for a, can you see? I just came right back to the fundamental theorem of calculus. Okay? This line here is exactly this line here. Right? The fundamental theorem. So what does it mean? Well, for me, I think the easiest way to think of what it means is to look at this piece right here. What does that tell me? Anyone want to interpret this? I think it's much easier than you think. What does dA dx represent? The derivative of a. And the derivative of a tells me, good, the rate at which, and a represents area. So this is the rate at which the area is changing, right? What does it equal? The function, f at x, which in this picture is the height of the curve. So really all this is saying is the rate at which, let me bring this picture back, the rate at which this area is changing is equal to the height of the curve. The rate at which the area under the curve is changing is equal to the height of the curve. Or the rate at which the area under the function is changing is equal to the value of the function at any given position, at any given location. Does that make sense? What if the function was really high? What if f at x was way up? What would that tell me? That a is changing very fast. Does that make sense? I think it does, doesn't it? Because it means if I move over a little bit, I'm building a very big rectangle. I'm adding a pretty significant chunk of area. What if f at x is very close to the t-axis? Yeah, that means that f at t is going to be very small. It means that my area is changing very slowly. And that also makes sense because if I'm down here, if I move over to the right, I'm just adding a very small rectangle. I'm not adding very much area. Does this make sense to you? dA dt dA dx equals f at x. In other words, the rate at which this area is changing is equal to the height of the function. Make sense? That's what the fundamental theorem part 1 tells us. That's what it means. Okay? We already know how to get the answer. That's easy. We just substitute in the x. If these things don't work out, we know how to deal with those 4 situations. Getting the right answer, I think, is easy. Understanding what it means, I think, is a little harder, but that's basically what it is. It's saying, now I know that if I've got this red area, but remember, this is a variable, then what it says is, if this thing is going that way, I'm accumulating more area. Can you see that? You can appreciate that, right? If this is going over like this, my area is growing. How fast is my area growing? Depends on the height of the curve. If the curve is very high, I'm accumulating area quickly. If the curve is very low, I'm accumulating area very slowly. How fast the area is changing, how fast the area is changing depends on the height of the curve. I get the impression you're still a little bit unconvinced. Andreina. It doesn't, but if the upper limit is not a variable, then I don't have a rate of change. Right? If this is a 2 and this is a 5, then how fast is the area changing? It isn't. Right? The integral from 2 to 5, the area between 2 and 5 is a constant. It's not changing at all. But if this is allowed to move, then I have an area which fluctuates, which changes. Make sense? Let me try it this way. Suppose I told you that the height of this curve was 6. Okay? What does that mean? If the height of this curve is 6, can anyone interpret what this would say? If the height of the curve was 6, what would dA dx be? 6. What does that mean? Yeah, it's a great answer. A small increase in x will produce a 6 times that increase in area. In other words, if this is a height of 6, if I move 1 pixel to the right, I accumulate 6 square pixels of area. Yes? If I move 1 millimeter to the right, my area grows by approximately 6 square millimeters. If I move 1 centimeter to the right, my area grows by 6 square centimeters. If I move 1 meter to the right, really? What's happening here? It's starting to get pretty bad, isn't it? Right? I mean, this works for infinitesimal jumps. If I move a small amount to the right, my area increases by 6 times that amount. If I move a lot to the right, not so much anymore. Right? If I was to go 1 kilometer to the right, right, that puts me, down there a kilometer. Where's my curve? It's going to be a kilometer in the air, right? It's going to be growing a lot faster than what it is right now. Make sense? In fact, you can see, even with this dx, it's not true, is it? The increase in area is not the area of this rectangle because I'm missing this little corner, right? But if this rectangle is small enough, then this corner vanishes, right? Becomes vanishingly small. And so I get exactly the right thing, okay? This is, remember, talking about an instantaneous rate of change. That's what derivatives give me. This is telling me the rate at which the area is changing right now is 6. Tells me if I go a little to the right, my area increases by 6 times that amount. If I go a lot to the right, all bets are off. Does that make sense now? Can you see it from that perspective? Because I think it's not that bad if you can think of it that way. All this is doing is telling me how fast I'm accumulating area as my upper limit of integration is allowed to move. Yeah? Any questions? Fair.
So is this kind of like the inverse of the slope getter function of the area getter?
Yes. Yeah, that's a nice conclusion. We're going to get there in about 2 minutes. Okay, but that's great. I like where you're going with that. You're exactly right. Anything else? Let's have a look. Before we go on any further, let's deal with this problem of why do we need two variables. Nobody asked it. I sort of expected somebody would. Okay, I suspect some of you were thinking of it. But does it not bother you at all that we've got an x in the upper limit of integration and a function of t? I mean, that should be a little awkward. It seems a little awkward. And one of the questions that I get asked a lot, that I've always been asked a lot, is why do these things have to be different? Okay? And I'll be honest with you, until about 6 or 8 years ago, the standard answer was they just do. Okay? Just deal with it. They just do. It's not written in the textbook, but I didn't like that, and so I spent some time and I thought about it, and I think I've got this worked out now. So I'm going to try and explain to you why I think we need two variables. So let's start by looking at this. The integral from 2 to 5 of t squared dt. What does this represent? Sure, the area under the t squared graph from 2 to 5. What is my answer going to be? What kind of a thing? It's going to be a number, agreed? In other words, I'm not going to get a t in my answer. Agreed? We say that t is the variable of integration here. And we say that this is called a local variable. We say that it's a local variable because it doesn't come in our answer. Okay? If I actually work this thing out, how would I work this out? Take the antiderivative of t squared, which is a third t cubed, and then evaluate it from 5 to 2. Right? Remember, this thing is the same as this thing. The 2 and the 5 refer to t's. This is saying that t is going from 2 to 5. It's implied. We don't have to write it, but it's automatically there. It's like saying if I write the square root of x, I don't need the little 2. It's already there. If I want to write log base 10 of x, I don't need the little 10. It's automatically there. The same is true here. That 2 and 5, this 2 and 5, we know that this means t equals 2 to t equals 5 because this is dt. Okay? And like we just said, we take the antiderivative, we plug in the numbers, we get 117 over 3. Yeah? Piece of cake. Graphically, what does it represent? Well, it represents exactly what someone just said. The area under the t squared graph from 2 to 5. It looks like this. And we say that that area in there is 117 over 3 because that's what we just found out. Okay? This is fundamental theorem of calculus part 2. This we've already dealt with. Now let's think of this one. The integral from 2 to x. Well, this is a different kind of thing. Do you see that? This is going to have to be called a global variable because I'm going to get an x in my answer. Am I not? How would I actually solve this? I mean, if I gave you this question and said, what does that equal, what would you do? Same thing. Antiderivative, put in an x, put in a 2, and I get this thing, and this thing, fair pawns. This function of x is effectively an area getter function. That's what that is. Okay? If I put in a 5, I get 125 minus 8 is 117. Over 3, I get exactly what I thought. Okay? And it looks like that. Make sense? Okay. I had a closure activity for you. Actually, it's break now. I'm going to do the closure activity. Okay? So, let me just finish this up. I'm sorry I'm going to eat a little of your break, but I want to get to the end of this. Let's think about what would happen if we didn't have two variables. If all of this was x, then I would have x here, x here. This is x is going from 2 to x. X is going from 2 to x. Do you see how ludicrous that would be? What would my interval be? What would x be going from? X would be between what? What does it say? X is between 2 and x. Do you see why that's problematic? You see what's going on here? These are two different x's, aren't they? Really. This one is saying, as I'm moving across, what's happening to my area? As my vertical line is moving across, I'm accumulating area. That's what this x is. This x is saying how far I'm allowed to move across. See how they're two completely different things? That's why these can't be the same. Doesn't make sense. Okay? I've got a more complete explanation of this posted on EDU 2.0, so you can read that. It's a couple of pages of why we need the two variables. If you're interested, if you're not, it's not really that crucial. Okay? Closure activity. Tomorrow we're going to answer the question, remember, why do we care? Okay? How does this help us? Closure activity, very quickly. Let me just take this off. Take 30 seconds and answer that question. Horacio, what'd you get? Give it to me in the first step first. X cubed. Uh-huh. Okay. Quick check here. Thumbs up if you got that. Thumbs down if you didn't. Why don't I do the what? Because the rule says this goes in everywhere there's a t, and then I take the derivative of this. This is my box. Okay? Everybody good? I know what you're thinking. Don't worry, I didn't forget you. The part in red is the new stuff, so that's what you've got due for tonight, page 287, 37 to 42. The other stuff in purple is what I've assigned so far in this unit. Okay? You should make sure that you've got that caught up if you haven't already. Okay? That's it. Thank you. Sorry I went a little bit late. And I will see you tomorrow as we will find out why we care about this.